honored to welcome Professor Eng this morning. So currently Professor Eng serves as the head of science, mathematics, and technology at Singapore University of Technology Design. Some of his research interests include charged particle and laser interactions with different 2D materials and other structural components, as well as some plasma modeling and other various other experimental and theoretical works. A few of his honors include being named a fellow of IEEE, fellow of IOP, and an IEEE NPSS Distinguished Lecturer. And so with that, I'll hand it over to Professor Eng if you'd like to give any other introductions, and we're really excited to hear your talk this morning.
Okay, thank you for the introductions. I just noticed that when I was a PhD student in Michigan back in 1994, so it's almost 30 years. So time really flies. Okay, so yeah, it's quite amazing. Yeah, so I'm very pleased to share about my research today with all of you. My advisor was Professor Y.Y. Lau, and I collaborate with Professor Ron Gilgenbach quite a bit with his group in experiment back in so-called the plasma bay. So let me share my screen. Hold on. Okay. Okay, my name is Ricky Ang. So I suppose all of you can see the screen. Okay, I'm right now working in the Singapore University of Technology and Design. This is the fourth public university in Singapore. It was set up in 2010, about 12 years ago, with the collaboration with MIT. So my topic of my work was actually strongly motivated by Y.Y. Lau works back in 1995. While the work is not related to my PhD thesis, but you can see that it carried the favor of Professor Lau in formulation and the integral scaling law. Happy to share that even though I like experiment, but I don't have talent in experiment, so I stick with computation. So my work is basically focused on the basically formulation, and we also have a set of computation tools to simulate all kinds of systems. Basically, we deal with electrons, we deal with charged particle, we also deal with laser. So the funding has been funded from Singapore and US. Currently, we still have an ongoing office naval research work through the Japan office. So the topic, I'll give an introduction, what is electron emissions and the motivation why we are doing that. So it's a very old topics, but I did the works in 2015. Basically, we look at all these new quantum materials. I think most of you heard about graphene, MOS2, all these materials. So the basic question is whether the emission models need to have revision based on this unique material property. And of course, we look at thermionic emission, field emission. Then, of course, we look at photo emission. The last topic is something quite interesting, funded by the Navy Research Lab. If I have time, I'll go through very quickly. It's something about fractional calculus. Then I conclude with a very quick table in summary. So if you look at the history of electron emissions, actually Richardson law developed a model back in 1901. The work won the Nobel Prize in 1928. Basically, the physics is basically you have electron on the metal surface. You want the electron come out from the surface, you heat it up, right? So this is like a filament, you heat up to high temperature, typically a few thousand Kelvin, the electron come out, all right? Then later in 1928, when the quantum mechanics have been mature, Fowler and Norheim, two scientists, I believe, back in UK, they're basically using a simple model. Consider if you apply a field high enough, right, the electron, even at room temperature, they will be able to tunnel through, right? So this is the famous so-called the Fowler-Norheim law. So if you look at this equation, even though the physics is different, the temperature, one is due to temperature, one is due to field, but if you look at these two equations, he actually have very similar form, right? You can see it's T square, you have F square, and then there's an exponential term. Then of course it depends on the work function, right? If your work function is higher, this exponential term will actually very, very small. So meaning the current emitted will be very small. Then of course you can see that on the bottom on the exponential term is also temperature, also F. So I will explain that actually this uniform is due to we are studying the traditional materials, so that the energy dispersion relationship of the material is basically follow something called a parabolic dispersion relationship. So there's a key assumption that need to revise if you're using graphene or simple many of the 2D materials. Then if you look at photoelectric effect, we know photoelectric effect by Albert Einstein, 1905. Then of course we know that if you right now have a work function, which is, for example, need multiple photon to absorb to come out, is called multi-photon absorption. Then you can see the proportional constant of the number of photon absorption is also square. So we are among the three model, we are quite sure that the thermodynamic and field emission model have been quite well studied by my group and others for the past 5 to 6 years. Photoelectric effect, especially due to ultrafast laser, there are still some problem remain unsolved. Okay. So I'm not going to go to the formulation. I just want to present a high level kind of results. But for those of you, if you want to understand what is the traditional electron emission model, there's a good book by Dr. Kelvin Jensen, who is a scientist in NRL. Actually, he's a good friend of Professor Lau. Okay, this book I forgot, 2018 is a very good book. Okay, so even though we are looking at electron emission, I know that most of you here may not come from an electrical background. Since I came back to NTU, I came back to Singapore because Singapore there's no nuclear engineering. So my work is basically working in the electrical engineering department. So you can see that if you look at electrical engineering department, if you take a metal and then you make a semiconductor connect together, there's an interface, right? So imagine that this semiconductor is almost like insulator, right? Okay, just imagine that basically there's an interface. So you can actually using the same calculation to calculate what is the electron emitted from the metal into that interface. So same thing, if you look at their literature, they also talk about thermal emission, field emission, photo emission. Okay, then there are equation known as a so-called Sofsky diode equation, even though they are from the different community, but basically the physics is the same. So other than look at plasma and vacuum electronics, that YY and defense people in US are interested, for electrical engineering, for solid state material, since right now they are using two-dimensional material, right? They can actually make, like for example, this semiconductor to be a graphene, single layer graphene. So the question is, all these so-called solid state equation, will they be valid? Okay, so it's the same principle that I'm looking at this problem. So in terms of technological impact, why this is very important for all of us using transistor, right, computing. So silicon technology comes to the end. So in order for you to actually increasing the frequency of the devices, the device getting smaller and smaller. So the ideal case is if right now your channel is basically become like a single layer graphene, then you put two metal electrode, then you control using the metal electrode to control the voltage. Then of course, for any devices with this interface, there are something called contact resistance, meaning that you apply a voltage difference, then you ask how much current is being passed through. So there's a quantum limit of the contact resistance that how slow he can go through. That's so-called the quantum resistance. So the engineer and material scientists have been trying to push to this area. So if you look at this is back in 2015, if you look at the ITRS, this is basically a roadmap for the development of semiconductor. In order for them to produce a transistor that operating using two-dimensional material, right? I list out a few of them here. The contact resistance actually have to go to the lower right bottom. Okay, so you can see that the contact resistance actually have to be very, very small. So which means that you need to emit a lot of charge at a very, very low field. So that is the motivation in terms of the technology impact other than physics understanding. Okay, so let's go through one slide showing graphene, right? So graphene was developed, okay, by Andrew and Professor Kovos back in Manchester. They eventually won the Nobel Prize in 2010. Happy to share that Novoslavov right now, he is a professor in National University of Singapore. He joined Singapore about 2 years ago. So basically, if you look at the material property, why graphene is interesting, because right now the electron in the graphene travel along the graphene, right? Meaning a very thin layer of material. In terms of quantum mechanics, he basically behaves like a Dirac, so-called mass-free Dirac fermion. Okay, meaning that the electron almost behave like no mass. There's still finite mass, but the mass is very, very small. Okay, he also moves very high speed. And then for those of you who know matter, you have something called Fermi level. Due to the unique property of the graphene, you can actually, using chemical doping or using electric field apply, you can control the Fermi level. This property cannot be found from the matter. You have finite density of state, and then most important thing is you can look at the energy dispersion relationship, meaning the E as a y-axis, K is a so-called in the x-axis. Then you can see very, very close to this Fermi point, you can see it's linear. So this property is the reason why it's different from the traditional material. It's always a parabolic. So let's look at thermionic emission. So in 2015, with my first PhD student in SUTD, he asked a basic questions. If you look at this graphene equation, all right, the A is an equation described by some constant, then also there's an effective electron mass. The problem about this electron effective mass for graphene is unknown because it's massless, it's very small. So many people using this equation to fit with the measurement, without really arguing whether the equation is correct or no. So we did a simple calculation just by replacing the parabolic energy dispersion with a graphene model. Then you can see that we are able to remove the dependence on M. Okay, of course, this model is simplified enough, but I want to draw your attention. The temperature scaling right now is T cube. The rest are simply fundamental constant. And then the Fermi level tuning appear in the exponential term. Okay, we call this is due to the momentum conservation. Later, I will show another model which is momentum non-conservation. So when we published this paper, the editor was kind enough to share one of the work from a Chinese group. He did the experiment. What they do is they're able to put a graphene, single layer graphene on a suspended carbon nanotube film. Why you need to have a suspended structure is because you don't want the matter property to influence the property of the graphene. Then by doing this experiment, we were able to show that actually the scaling of T cube is actually give a better agreement compared to the traditional model. So our model has been showing graphene, but we know that in a lot of experiments, the temperature property may not be purely T cube or T square. So we're using a model called Kane dispersion non-parabolic model. Basically, there's a tuning parameter called gamma. So if this gamma is very, very big, meaning this equation basically show a linear dispersion relationship, so the current recover T cube. If this gamma is 0, then meaning that this term is 0, there is a parabolic dispersion relationship, then the traditional model appear. So we are able to right now have a general model determined by the value of gamma. So what you can use for this model is you compare with the experiment with some material that is not purely 3D or not purely 2D. And then we try to fit the equation and then to find the value of gamma. Then that describe the property of this particular material. So after doing these two work, we start to see many experiments come out. Okay, they basically right now perform experiment based on two types of contact, vertical and lateral. Vertical meaning that, for example, you look at this vertical, meaning this is graphene, right? So if you look at graphene and semiconductor, you can see the interface between them is vertical. It's not at the edge. So we call vertical emission. But you have another structure we call lateral of edge. But you can see that this right now, the green one is the graphene attached with a semiconductor. Then you can see the edge is right now connected. So this is called lateral. So if you right now want to perform the measurement of the current, you have these two types of structure. Their experiment have shown that by plotting the measured current as a function of temperature, you can see this beta, the scaling constant can be 1, can be 1.5, can be 2, can be 3. So we wonder whether we can have a uniform model to kind of explain all this scaling. So we are able to accomplish this in 2018. This paper was published in PRL and quite highlighted quite a lot of by the medium. So basically, we report two universal scaling. Independent of what kind of 2D material that you use, as long as the energy is linear dispersion relationship for vertical contact, for lateral contact, the temperature scaling is 1.5, 3/2. So we able to have a general model to describe it, and we purposely pick out a few material to show. Of course, the constant will be different, but you pay attention to the temperature scaling. Everything is 3/2. Later, when you look at the field emission, you can see actually field emission also have this scaling when you are looking at HM emission. Then this is simply an example to show that experimentally they measure. So they basically make graphene MOS2 or WS2 MOS2. So it's different 2D material. They perform measurement and then indeed they recover 3/2. Then we look at vertical contact, meaning that the temperature scaling beta is equal to 1. Okay, then we also use a few material and then prove that the temperature scaling is equal to 1. Unfortunately, this temperature scaling for 1 have not been reported by experimental. For experimental, the H emission is actually more interested. Then our assumption have been used, consider the temperature have to be small, meaning that if you look at the full energy dispersion relationship for graphene, it's actually not linear. The energy dispersion looks something like this. Okay, so we call this kind of thing so-called full band-like diagram. So what we did is we are not able to get the analytical solution, but we basically create a numerical model to show. So this comparison is compared to the JD is the linear dispersion model compared to the FB. FB is a full band model. We can see that as a function of work function and also as a function of temperature, these two curves actually agree quite well, fit well, which means that the scaling remain valid, but the magnitude may change, right? It's due to, because right now you have to consider the high energy electrons. So let's move on to field emission. So again, you can see field emission, the beta is equal to 2, right? F squared. So we first of all, we want to look at 3-dimension material. We call 3D semi-matter, okay? So the energy dispersion sheet is different from the traditional 3-dimension matter, but you can see that when we're using a proper formulation, the alpha, meaning here, instead of using beta for temperature, for field, I'm using alpha, it's become 3. And then we actually list out 3 of the material that experimental people have fabricated. They measure the work function, they know their Fermi energy level, then we simply calculate how is the field emission current. And then we prove that actually is F to the 3, indeed. Of course, this one require experiment to prove. This prediction was done back in 2021. Then other than 3D, we do a 2D, right? And then for 2D, remember this is for vertical emission. Just now when you look at the vertical emission for temperature, right? T is equal, beta is equal to 1. Again, we recover that the F is indeed beta is equal to 1, similar to the thermionic emission. And this paper will be published as an invited paper in the physics of plasma sometime this year. Last year, we did a review to analyze, okay, all these two-dimensional material, is it a lot of people do the field emission? So we collect a lot of, it's like a review paper to celebrate the IEEE transaction 50 years anniversary. And then we show that actually, indeed, if you look at the application, the current can actually quite significantly. And then the field enhancement is actually very, very big. And then compared to two-dimensional material, the topological material is actually very little. For what we found is actually only 2 of them. Okay, so this paper is simply try to encourage experimentalists to work with material scientists to get the material and then perform the measurement. Then this one I go through very fast, simply because for the defense. So for defense, you want to have very, very high current. And then normally we know that there's something called spatial limiting current. So this is actually triggered by YY paper. I believe this is the first paper I read when I was a student with YY. So basically, when you have a field emission and low field, he follow the Fowler-Nordheim law. At high voltage, he actually will follow something called Char-Lamiel law, right? Lamiel actually won the chemistry Nobel Prize back in 1930 something as well. So since right now we know that the field emission for two-dimensional material, the prefactor, the power law may not be 2. So we simply using YY approach, and then we calculate what happens if right now the prefactor K is not longer 2, can be any value. And then indeed, we already shown that experimentally and calculation-wise, therefore that for example, for graphene, for nanowall, and for other things, indeed this K prefactor may not necessarily equal to 2. So we perform the calculation, and then I just summarize. We found out that if right now your K is less than 1.5, you will have a regime on the left-hand side when the gap spacing is small enough. Doesn't matter how high your electric field is applied, you will only have field emission. You can never reach the spatial limiting current. Okay, so this understanding is actually kind of unthink of at the time, but the physics actually very simple. Because the field emission actually do not able to emit enough current to produce a spatial field high enough in order to solve the Poisson equation, right? So mathematically, that is the reason. Then we also show how is the transition for different kind of material. And then this was a recent paper published in 2021 as well. So I think some of you are interested in using ultrafast laser, especially we have very good ultrafast laser back in Michigan. So this is a new topic. I studied ultrafast laser probably 10 years ago, but at that time I focused only on metal. Okay, so basically for those of you, you know there's something called Keldysh parameter. If you apply the field F, it's very, very big. Then this Keldysh parameter gamma will be very small. Okay, so the F is very, very big. So this gamma, okay, I think there's a typo here, sorry. Okay, so it's the other way around. Okay, so when the F is very, very big, then gamma will be very small. Then it's so-called optical tunneling. Sorry about the typo. Then if right now your F is very small, you apply the laser field is very small, then the gamma will be actually very, very big. Then it's so-called the multiple photon absorption. So this is a very famous Keldysh parameter in physics. Then many experiments actually always perform the experiment at the region of gamma close to 1. So for example, the typical laser that you use is 800 nanometer, 6 to 54 femtosecond, very low power, right? So that the material was not break down. So the idea at that time was, what is really the mechanism when your gamma is close to 1? So we including 2 physics. The first one is because the laser pulse is so short. If you heat up a material, the material take time to heat up. So for metal, it typically take more than 1 picosecond. So if you right now using a femtosecond laser, your metal actually right now, under the excitement of laser, your electron temperature and your lattice temperature actually right now are different. Okay, so that is so-called the non-equilibrium heating. So electron is actually hotter than the material itself. So we're including this effect. And also we including this for matter, so there's no 2D material. So we including this effect, and then we actually write a code to solve about 150 time-dependent Schrodinger equation. Then you can see that our model, the black color one, solid line, is actually improved compared to the previous model. And then we actually able to show that the critical gamma, remember this gamma is close to 1 during the transaction between these two regimes. And then we found out that actually we show that there's a formula at this critical transition, gamma is equal to 1.18 times the work function of the matter. So if using the work function around 4.5 to 5 for gold and silver, then you can see that our calculation show that the critical parameter is about 2.5. Then experiment have shown that this transition is around 2 to 3. Okay, so again, this is a very old paper that I did before the 2D material was so-called famous. Then we also show that if you right now you make your laser pulse very, very short. For example, if you look at a 8 femtosecond pulse for 80 nanometer, it's only 3 cycles. Okay, so 3 cycle laser pulse, if you're able to do a 3 cycle laser pulse, if you compare to a laser pulse, is 20 femtosecond. If you look at very, very low field, Albert Einstein photoelectric told you that you need 3 photons. But if you right now reduce the laser pulse length to 3 cycles, you only require 2 photons. Okay, so this is based on calculation. And then we actually suggest if you want to perform this experiment has not been approved. This is actually my largest regret. I believe this is true. If you take a material of 3.9 EV, laser pulse is 800 nanometer, and then this diagram actually show you where is the transition. Okay, so if you're able to find a laser 800 nanometer, which is the common laser, find a material, helium. I think this may be a material have highly radioactive. I think all of you should know, right? So it may not be very safe, but again, this experiment will be interesting to conduct. I think the next 2 slides I will pass is basically talking about plasmonic effect. Okay, not important. So I look at we recently, this work was not published. We just saying, okay, what about we replace the metal with graphene? So you can see that right now the energy dispersion is linear. It will go through. Then of course the laser pulse right now is changed very fast. So there's something called Pondermotive force. So we perform the calculation. We able to write the equation into some function which is not very popular. It's actually created by Mathematica. Okay. Then of course we like what YY did. We normally want to make assumption to make the model correct. So we consider, for example, you look at very low field, we're able to simplify the calculation. Again, this is for edge emission because you shine the ultrafast laser at the edge of the graphene. The graphene is very thin, so the field enhancement is very high. So you want to have a local field very, very high, but you don't need to have a very, very high power laser. So the graphene will not be destroyed. Okay. So we can show that again. Remember, you recall the temperature scaling of 1.5, and then for field laser, we see also you were able to have proportional to the laser field of 1.5. And then same thing, if you right now do very, very high field, you can see that it's actually there's a saturation effect. So you may say, oh, this maybe it's only for graphene, but indeed it's not for graphene. It's actually general true for a wide class of 2-dimensional material that we're using this general equation to describe. And then all these equation basis show that you can see that the power is simply equal to 1.5. And then current are all saturated. Okay. I don't know how much time that I have. Can I have maybe 10 more minutes to close it?
Yeah, we've got an hour blocked out for you. So yeah, 10 minutes would be great. And then we can move on to questions.
Okay. So then we using our model to compare with the experiment. And then it turned this experiment published by other people turned out to be quite well. And then we also show that for application, you can actually have tuning your DC field or tuning your laser field. They're able to, you can control what kind of current that you have. Then for ultrafast laser, you can see that the electron is actually emit only on a half cycle. And then there's a maximum of the electron energy. If you measure the electron emitter as a function of energy, each of them also has a maximum energy. Then we can actually calculate what is the maximum energy that you can get. So next 5 slides, very easy. So all these are very ideal. Your material is considered flat, but we know that for real application, the material is always rough, especially if you bombard the material with a laser for many times. So we're using some approach called fractional approach. Basically, you're using some mathematical technique. You calculate this particular surface, and then you consider this is like a fractal. For example, instead of a 2-dimensional surface, this surface, the dimension is about 1.705. Okay, because of the roughness, it's a fractal. And then we treat this particular as a object as a 1.7 dimension thing. Then we solve the equation in 1.7 dimension instead of 1 dimension, 2 dimension, 3 dimension when you do your calculation, right? So what I learned is I learned from the mathematical tool developed by mathematicians, and I'm using their tool, and then I simply solve it. So you can see that the field emission right now, we actually have a parameter called alpha that actually can classify the roughness. Okay, then this is another comparison with the experiment for thermionic emission. Then you can see this characterization, this roughness is alpha equal to 0.934. Alpha equal to 1 will be a perfect flat surface. Then this is like a junior year physics problem. You want to calculate what is a flash laser absorption through a metal surface, right? We consider right now surface rough. Then we perform the calculation, okay? Then the solid line is the calculation. The star are the experimental result from other people. This is restricted for metal. And then you can see the agreement is very good. So this fractional calculus is actually very general. As long as you have any equation, I will be able to solve in the fractional dimension to help you to characterize your experiment. And then this is simply summarized for what I did. We pretty much only have one last part, the photo emission for the multi-photo emission that we have not have any result yet. So I believe that 1 or 2 more years, the review of this emission law for 2-dimensional material will be complete. And then this is a list of paper that review paper. If you want to understand this, get started, this will be quite a good paper. As you can see, YY was co-author in one of the paper. Okay, thank you very much. And this is our campus. If you happen to come to Singapore, it's very close. It's only 10 minutes drive from the Changi Airport. Yeah, thank you very much.
Right, thank you. Right, yeah, so first, let's give a hand for Professor Ng. That was a great talk. And yeah, with that, I guess we can open up for questions now. So.
Yeah, sure. I can start it off with, hold on, there we go. Can you hear me? I can start off with a more general question. It's a bit out of my expertise, your talk, but it was still very interesting. But more generally, the thing that I was seeing in your presentation was, you're driving quite a few physical equations, but it seems like when you adjust for experimental data, it may be some more empirical adjustments. Can you speak a little bit more to that, and how much those play in each part? Like how much of it is based on theory, how much of it is empirical?
Yeah, so if you look at the scaling, if you look at temperature scaling, F scaling, the power law, that one have to be valid because this is due to the materials and due to the physics. Normally in front, the constant, all these things can be due to many things because the model is 1 dimension, is current per area. So a lot of time people may perform the experiment is total current. And then in order for me to know what is current per area, experiment people may not able to spot the emission area, that kind of thing. Yeah, so I think the scaling is important because once you compare with the experiment, you can kind of fit the equation with the experiment result to get the constant that you need for. Yeah.
Well, thank you, Professor. Any other questions?
So yeah, I can go next for this one. One of the things that I wasn't super familiar with is the idea of fractional calculus. So I was just a little bit curious, like, especially when we talk about things like 1.5 dimensions, are those purely empirical and are purely for the sake of modeling, or do those have like a more physical implication, like, or more like, I I guess what would be the physical intuition for those kind of numbers?
Yeah, so the fractal is real. So actually in the world, the fractal is more real than the 1D, 2D, 3D, right? So okay, if I may, okay, let me just, if you have time, I just share one slide. I prepared this one for the
Please
fractal.
go ahead, Professor.
Is it okay for me to share the slide?
Yeah, absolutely.
Okay, let me see. Okay, I screen this one. Hi. Okay.
Well, Professor,
Okay.
that slide.
Can you see the slide now?
We can see it. You're still in PowerPoint editing mode. If you want to share slide.
Oh, okay. Sorry.
No, that's okay.
I should close the other one and then share the new one. Share the screen. Okay.
That looks
Can you
good.
see this? Yeah. Okay. So how do you define dimension? Oops. Okay. So everybody know 1, 2, 3, very familiar, right? So basically the dimension is basically talking about, you take a box. Right now you divided the box, for example, the middle one, the blue one, right? So you look at the small box. So the small box, you can see that the self-similar pieces right now, how many of it? 1, 2, 3, 4. Am I right? Then the magnification factor for each side is equal to 2. So you take log 4 over log 2. That define the dimension of a square is 2, right? Same thing for a cube. You take, for example, this one, right? Is log 9 divided by log 3. Okay, so for example, sorry, this one, right? Is also 2. So similarly, you take a cube, there is log 27 divided by log 3. This is 3. So let's assume there's another object. You take a piece of paper, you draw a triangle. Then on each side of the triangle, you cut into half. Consider this is a paper, okay? Then you draw an empty triangle. You take the middle part, the paper out, you throw away. Then you repeat the same process again for the other 3 small triangle. And then you keep doing it, Then you're using the definition of dimension mathematically. Dimension cannot be defined by your eyes, have to define by equation, okay? So by this particular structure, you can see that every time that you do, you only have 3 pieces left, right? Because the middle part you throw away. And then the magnification factor from each side is only 2. So log 3 divided by log 2 is 1.58. So for this object, it's actually a 1.58 object. Because it's not a perfect piece of flat paper, okay? So same thing, this is called suspensive carpet, right? Or suspensive triangle. If you look at the merger sponge, same thing, you divide it into each side 3, then the middle hole you always take away. Then you can calculate, right? Total is 27 minus 7, because 7 is the one that you take away. Each side, the magnification is 3. So it's log 20 divided by log 3. So for this object, is 2.727. Yeah, so basically the dimension is real.
Okay.
So when you have a surface that just now I show you, there's something called box counting method that mathematical developed. You can define that object effectively mathematically. What is the object? Then if this object, you know what kind of dimension already, right? Then when I solve that equation, I don't solve 1-dimensional equation or 2-dimensional equation or 3-dimensional equation. I solve the equation in that dimension, fractal dimension, using fractional calculus. So that is actually the technique developed by mathematicians. I just simply use this. I only learned about fractional calculus when I was very old, 2016. Am I right? So old guys still can learn things. So, so basically, just to tell you, it's real. I don't have time to present. I actually using this technique to present much more, a lot of things, fractional capacitors, any equation. If you right now have a dimension that is not perfect, I will be able to solve it mathematically. Then we'll see how and then compare with the experiment result. Yeah.
Thank you, very interesting.
Yep. Yep.
Plus, did anyone else have a question? I had a follow-up, but yeah. So I know you, along the same lines, you mentioned going from the more ideal models to a more realistic system would involve taking into account things like the actual surface roughness. Are there any other major topics like that that you foresee as like another barrier from or another thing to be accounted for to get like the most realistic real world models for some of these emission equations?
Yeah, there's another thing that's interested in is about the time. So if you look at the dynamic of the system, am I right? For example, you solve F equal to ma. Basically, what you are telling is the dynamic of that particular object you study. There's no memory. He only care about the instantaneous property at that time. But in the complex system, there are many systems that actually remember. They're not depending on that instantaneous time. He actually have a memory effect depending on some time previously. And then in order for you to simulate that kind of system, the easiest ways for you to do this kind of thing in physics is called non-locality, meaning that the property of the system do not depending on the local time. It depends on the history of time. And then in order to solve this kind of problem, a mathematician has been using this kind of solving. Consider the time right now, like for example, d over dt. You solve maybe d half over dt or something. Then that will be able to capture this kind of so-called memory effect. So you have to look at the system. If your system right now do not respond instantaneously, then quite likely you carry the memory effect. Then calculus is such an important tool for us to simulate the real system. And then again, fractional calculus, simply because of our education, none of us learn fractional calculus during our education. So it remains as a toy for mathematicians, but it's getting much more and more and popular simply because the computing power is so powerful right now, right? You cannot solve by hand, but you write a code, ask the computer to solve it for you. Yeah. So I think the potential is high. Yeah.
All right, thank you.
I had a question.
Yeah.
So in the end of your slides, there was a graph where you compared experimental and your theoretical data. Could we go back to that slide by chance?
Is it the laser one?
Are
my slide still right now on display?
Not right now.
Not right now. Okay, so hold on.
Is it the one with the platinum as the third graph?
Possibly. It's like 3 or 4 slides from the end, I think.
Okay, hold on. Let me.
Yeah.
It was,
Yeah, this is a slide, right?
yeah, I was wondering if there was a particular reason why in your gold experimental model that there were so many measurements taken around the 0.7 region for alpha and the 0.3 absorptivity.
Yeah, actually, we did not conduct the experiment. The experiment are from the paper highlighted here. So I think we just being honest. We just take all the experiment that's from the figure, and then we just plot our calculation.
Okay. I was
Yeah.
just,
Yeah, I don't know. Quite likely, maybe experiment perform multiple calculation at that particular roughness or something like that. I do not know. So we did not ignore any experiment. All the symbol are actually experiment from the paper. Then we simply just plot the comparison. Yeah.
okay, I had, I guess, one more follow-up question, which was, does by chance like material defects affect your photo emission spectrum, like your emission that's generated from your
Yeah, definitely. So far, the two-dimensional material that I use have been considered there is no defect, meaning it's ideal. Energy dispersion, all these things are very, very ideal. Okay, so that is actually the reason why two-dimensional material remains still difficult to be massively commercialized other than graphene. Because other material, when they grow, sometimes I was told that you grow 10 sample, maybe only 1 work. Okay, So I believe that the defect remain important. So in my model, I did not consider any defect. If I need to put the defect, I need to do something called density function calculation. I really need to calculate the material property due to defect for that particular aspect. Then same thing, I need to put into the model to calculate. And then most likely you will not get an analytical solution. It will be a numerical solution. Yeah.
Would like loops be one of the main material defects that you would observe from the laser, or would there be like other material defects that would be like really high in prevalence?
So far, the experiment that I've seen, the report for the measurement, they always consider their defect is very good, meaning no defect. So that they can say that it's a linear dispersion. Some of the common defect, for example, it turned out that graphene, if you do it correctly, is actually quite insensitive to the impurity, air or hydrogen, that kind of thing. So the surface dangling bond, all these things, they probably do something to clean it up. So a lot of time is due to the, for example, the nitrogen doping or oxygen doping on the surface. Then of course, because it's single layer, for single layer material, there's totally meaningless for you to talking about what is the inside so-called impurity, because only one layer. Okay. So it's impossible to define that. Yeah, I don't know whether I answered the question. I'm not a material scientist, probably not very good. I'm not experimentalist, so I don't know how good are their ability to do the so-called the doping concentration.
Okay, thank you. Appreciate it.
Yeah, probably not answer your question much. Yeah.
Professor, I have one quick question for you, going back to the thermodynamic emission equations. In particular,
Photo emission, is it?
Thermodynamic emission, like very early in the presentation.
Okay, thermodynamic emission, yes.
Mm-hmm. Yeah, I guess it's more a question of motivation and intuition. Specifically, I was curious to know what the motivation or what pushed you to do this new experiment and prompt this verification in the first place with graphene? Was it just a way to verify graphene's properties, or were there specific things that graphene presented that made verifying these models important or relevant?
I think for, let's say, if you look at electron source, metallic material may not actually still, if you look at the electron source, which is very big application, I think nobody is using two-dimensional materials. Okay, simply because you are hard to grow a two-dimensional material at very large area. Okay. Mm-hmm. I'm just guessing, I'm not experimentalist, but most of the time when a new material come out, for physicists like us, the interesting thing is to see what is the new thing that this material will affect the current understanding. So at the beginning, I believe it's more like just understanding. Okay.
Sure.
Then then for thermodynamic emission, I know that in China there's a group they make graphene into some very, very small emitter, and then they want to using the graphene as a emission for thermodynamic emission for a very, very compact emitter. Okay, from a Peking University. So that is an experimental group. They are working on it. Yeah. Meaning very, very small electron emitter. So the emission area maybe a few nanometer, that kind of things. Yeah.
Sure. Thank you.
Yeah.
Any last questions for Dr. Ng?
Oh, that was just me earlier. But thanks for saying.
Right. Last calls. Well, in that case, thank you again for the awesome talk. And again, we're very honored to have you, for you to give me your time this morning for us. Thanks again, and I guess one final round of applause for Dr. Ng.
Yep. Thank you very much. Yeah.
Thank you. Have a good one.
Okay, bye-bye. Yep.